Good. Greetings, students of the internet. My name is David Omach Tyson, and I'm presenting to you a small, we won't call it a lecture, we'll call it just a talk. And today I want us to look at standalone solar photovoltaic system sizing. So we've been pacing differently between students of Butere Technical Training Institute, where I am an active trainer. I offer a few lessons on the same at the TVET EDGE, and I have got now private students under the academy. So it's been back and forth, because I have different categories of students and different levels. Now the information might have been getting, the information might have been changing depending on the category of students that I'm dealing with. But for the general public and for the students who are doing their module 2, unit code name is install standalone solar PV systems. It's a core unit in module 2 for students undertaking their electrical engineering level 6. Now, the information I'm going to share today will be cutting across several major aspects, but it is the essential, we will deal with the essential learning material that a level 2 student is supposed to know. You can build from this information, because whatever I'm going to teach today will change over time. In our first session, we talked about the categories of loads, and the different loads, I went deeply into explaining to students that when sizing a solar system, the different categories of loads, depending on their nature, how they behave, the amount of time they have to stay on, will determine the other factors that will go into system sizing. So for example, we can have a refrigerator or a pump that will consume, let's say, 300 watts continuous consumption. But these loads will require an extra amount of current during startup. There will be a surge in the demand from the inverter or from the solar PV system. So when we are sizing our system, we have to consider that as much as this load has been rated at 300, during startup it will require more than what it's been rated for. And we have to include those factors when now determining the size of for example, the inverter and the battery bank. I went ahead and further explained that for standalone PV systems, most clients will not have these components on the standalone PV system. The standalone PV system that, according to the CBET developed curriculum that I'm supposed to teach, is the system that most clients will use for critical essential domestic loads. And these are not limited to, for example, the entertainment system, or what people call the TVs, radios. They might not be critical, but they're normally essential for the day-to-day running of a domestic dwelling. So a TV, a radio, we might want a client who wants to have their computers or their laptops on, they're working off grid. We might have a client who wants to have things like power backup to their internet or their CCTV system. So these are the kinds of loads that we want to size at this stage. As you advance, as you go ahead with your level of education, we will now come back again and learn how to size the same system, but to incorporate loads like water pumps, refrigerators, other bigger loads. We could have resistive loads, but now bigger capacity. So for now, you can deal with smaller resistive loads like small rice cookers that can consume an average of 100 to 300 watts. Those are okay. We can factor those. We can learn how to size those and include them in this system. But now when we go to the bigger loads like instant showers, which will consume up to an average of 3 to 5 or 6 or even 7 kilowatts, most clients will not invest in solar systems to do such loads. No. Those are loads that we have a specific category of clients which we will take care of when we now advance. So to begin with, I'm going to put up a small table that will guide us on how to calculate, number one, the total consumption if all the loads are plugged in together, or if all the loads might at some point be plugged in together. It's not necessarily that all the loads will be plugged in at the same time, but just in case all these loads that the client wants to put on the standalone system are plugged in to the solar system together, what is the size of the inverter that we need? Once we've determined that, we are also going to calculate the size of the battery bank. How do we size our battery to deliver this amount of power? For now, we will do with a single, or not even a single day, it's from evening to morning. For now, we will learn how to size a system that can support us from one evening to the next morning. As we advance, we will learn how to size a system that can go for more than 24 hours or more than 1 day of autonomy. For now, let's just learn how to size a system, a small system that can take us from one evening to the next morning where there will be sunshine. So in this lesson, we are going to learn how to calculate the demand and the battery bank sizing. So, okay, the demand, the inverter size, and the battery bank size in this lesson. And then in the next lesson, I'm going to teach how now to go back and calculate the charge controller sizing and the solar panel array sizing. And then probably in the last lesson, we'll learn now how to calculate the protected devices sizing and the cable capacity sizing. So I have grouped them in those stages so that we grow back to the panel. So in our first session, I gave my students, it was an analogy that helped the student understand that in system sizing, we normally start with the load demand. We don't just, when a client approaches you and tells you, I want you to come and give me the quote or the amount of money that I need to buy a system to support my loads. So what determines the amount of money that this client will need to buy his or her system? That is basically, essentially the maths that we want to try and learn today. So tag along. It will be a very shortest brackets, not to bore you, but if you are keen enough, you can go all the way until the end. Just be patient and listen all the way to the end, because there are some things that I might mention which I might forget during teaching now level 6 students. So let me first draw the table. You can take a piece of paper and do this practice with me. I'll list a few devices here or components that most clients will want to put on an off-grid system. You can add, you can remove, just for practice, and then we can advance from there. So now, why is this information relevant, or why is this information important? Someone might ask. As you advance in your career, because this is just the early stages of your career, but when you advance, the world right now is very keen on renewable energies and sustainable energy solutions. So you, as a technician, are at the forefront of empowering your local community first through solar entrepreneurship. Remember, in this same unit, we are supposed to learn a thing or two about entrepreneurship. How do you now apply the skills here in an entrepreneur role as an electrical technician? So to begin with, once you know how to do this, apart from sizing itself, it will also help you innovate affordable solar solutions. So, for example, there are a lot of appliances that we might have wanted to list here, but because they're normally heavy on their consumption, we have removed them. For example, we can, let's talk about fridges, for example. We have fridges, we have motors. Now in motors, I'm talking about water pumps. We can have fans in the house. These are technologies that most domestic users have, but might not find it necessary or worthy to plug them into a small standalone system because they drain more power. Hence, it means that at the end of the day, you'll need a bigger system to support very basic loads. So most people don't include them in the system. Now, the future of renewable energy is supposed to accommodate everything, right? But in this case, there are two values that we are going to look at, which will determine a lot of things going backwards all the way to the solar. The future of renewable energy is supposed to allow you to just do this irrespective of the load, size your system, and never have to force your client to spend beyond what they are comfortably capable of, but still delivering the renewable system. I have done the math. I hope it's correct. So on your piece of paper, I'd like you to spend the next 5 minutes. You can pause the video, zoom in, spend the next 5 minutes, draw this table. This is the appliance section. You list the appliances here. This is the consumption in watts. This information is normally found on appliances, either on the back of an appliance, or, for example, this is a laptop adapter. There's information here. So we normally look for this information here to use it to generate our values. So for example, this is a laptop adapter. It's been rated at 65 watts. We've rated ours at 60, which is still averagely okay. So some will go between 60 to 100. It's still okay. Just, you can find your adapter, pick this information. If you can't find, use any value between 60 to 100 for practice. The same way, even in indoor lamps, if you unscrew or unplug the lamp, it's normally written either on the side, you can find it on the box of the lamp. Most of this information is just readily available on the appliance itself. So pick this information from the appliance, the consumption in watts, fill it against the appliance itself. Now, the quantity of the appliances means one bulb consumes 10 watts. But a domestic dwelling can have, for example, on the indoor, if it's a 5-bedroom house, we can have on average at least 5 lamps. At least. We have got houses that have got decorative lamps, wall lamps. We have houses that have got probably the central lamp and periphery lamps. So pick this information, talk to your client, ask them, what do you want on solar? Because some might have those lamps, but they might inform you that if in case of a blackout, I can work with the central lamp. So that is what you put here. Put the essential loads first, the critical loads first. So indoor lamps, you can have 5 depending on what the client wants. Remember, this information, you're picking it from the client. You're not just generating it off-head. You're picking it either through an a visual inspection. You go around the house, you do a visual inspection. You can do an oral assessment, assess the client, know what the client knows about his electrical consumption first. If he or she is not giving you enough information, do it yourself, find out. Now, the total consumption here, the total consumption is equivalent to the consumption of each particular appliance times the number of appliances in total. So if, for example, we have got 5 lamps, you multiply the number, the consumption of each watt by 5 to cater for all the 5 lamps. For example, the outdoor security lamps, I'm using 7. You can use 5, or you can go around the house and determine how many they have. You multiply, you get the total consumption in watts. For example, that house might be having a laptop and a computer, or 2 laptops. So you multiply the consumption of each laptop by 2. You get your total consumption. Appliance times the number of hours. So again, this is another set of very important information, the daily operating time in hours. The daily operating time means how well or how much time does this client utilize these appliances. It's important because for every extra minute you plug an appliance to a backup system, in particular when it's not expecting to be charged or recharged anytime soon, you affect the overall functionality of the system. So for example, you might have a system that has got, I don't know if I explain it at this point. Okay, you might have a system, we might size this system, determine the inverter capacity and the battery bank we need for the system. But in this particular afternoon, the client has a charmer session at her house. And so she might end up having to charge, for example, let's say she has a charmer session of 20 women visiting her. And each, okay, not each, but let's say 10 of those women walk around with their phone chargers, each consuming between 5 to 10 watts on average. So let's use 10 watts because it's our starting value here. So you increase the quantity of appliances to 10. So 10 times 10 gives you 100. As much as the daily operating time won't be affected, the total consumption will increase because now this 100 times 4 will increase to 400. I hope you're getting what I'm arriving at. So we pick this daily operating time just to have a better perspective on the estimation will be able to guide us. It will take us closer to the 100% perfect system size. And we shall cater for that later on. I'll talk about how we put that safety factor or safety margin in our system. So the daily operating time, these you just have to ask, or you can estimate based on, as you advance, you'll know how to estimate some certain values. If you can't, just ask. Let the client tell you how much time do they spend making rice. If it's more than 1 hour, and you know some of these appliances, as you advance, you'll realize that some of them are not even being utilized on a daily. For example, a rice cooker might be utilized once or twice a week. So you just put it in there, but it's an advantage to you as a technician also. So once you've determined the daily operating time, now the energy used in watt hours is equivalent to the total consumption of the items times the number of hours. So for example, with our TV, one TV consumes 65 watts. We have two, so they'll consume 130 watts. And since these TVs will be on for 8 hours, we multiply by 8, we get 1040 watt hours. So this is the energy demand that is needed to ensure that our TVs will stay on for 8 hours. That is 10,000, not 10,000, 1,040 watt hours. Now, do this on your piece of paper, on a foolscap. I'd encourage you to add at least 2 or 3 more loads. You can comment down below how many other loads you added. Take a screenshot of what you've done. You can send it to WhatsApp. Our WhatsApp number will be appearing on the screen here. Send whatever values you've added or whatever appliances you've added and whatever values you get. Let's calculate it together after here because it's a learning session. So get these values and then let's proceed now to inverter sizing and then battery sizing. All right, now I hope you've done a few exercises with the values. So the first value we are going to break down further, the value under this section, this 950 watts, falling under the total consumption times quantity. So in our calculation, we've arrived at 950 watts. I hope it's the correct figure based on my calculation. So let's start. Remember, in system sizing, as I explained to my students on an earlier video, you can find it somewhere. It wasn't really deep, but it just captured a few components. In system sizing, we start from the demand. How many components are we going to plug into the system? We start from the demand and work our way back. So we've determined that we need to supply 950 watts at any particular point, or at some point in the life of this system, we will need to supply 950 watts. So these will guide the size of our inverter. So calculation number 1, inverter sizing. Now, we've calculated our values and we've gotten the two most consequential or determining values for our sizing process. At this stage, as a technician, for a standalone solar PV system size, you are comfortable in advising your client to get a 950 watt inverter, an inverter that can comfortably allow 950 watts to flow through it. This is the reason for this value. But we all know we do not exist in a perfect environment. And let's assume your client, one evening, or one weekend afternoon, she's a very social lady and she's receiving guests from her chama. 20 guests, and from the 20 guests, let's say 10 of them, or even 5 of them, let's be modest, let's say 5 of them carry their phone chargers, each worth between 5 watts to 10 watts. I mean the consumption in watts, not watt, the consumption in watts will be consuming between 5 to 10 watts. So if we add 5 extra units here, that becomes 8. And if we multiply now the 10 watts times the 8 units, we get 80 watts. That also means the daily operating time, it might stay the same 4, but this value will have an effect on the 950 watts. So what normally happens in this case, for a standalone system, we will advise you to introduce a safety margin. In most cases, it's normally 50% of what your system is supposed to deliver. The base value is 950 watts. The safety margin is 50% of 950 watts. So our safety margin, if we introduce 50% extra, if you're fast enough, you can comment before I'm done. All right, that is 475 watts. So this 475 watts is the safety margin that we need to add onto this inverter capacity for it to operate safely, just in case the values that, or the components or the appliances will be increased, or the number or the quantity of the appliances will be increased. It is important to note that 950 watt is our first answer. So the inverter sizing, the base value, as a student, make sure you're informing the invigilator or the person marking that you are developing your value step by step. So the first value, the base value of the inverter is 950 watts. So you write the base value 950 watts. So that means if we get a 950 watts, we are getting our client all these appliances plugged in safely. I also share that there's no manufacturer that will give you an inverter as a component and just limit it. If, for example, they've manufactured the inverter to deliver 1,000 watts, that inverter has got a reasonable surge capacity. That inverter will be able to deliver 1,000 watts comfortably, but then it will give you an extra percentage, probably 30 or even 50%, so that in case you plug extra devices to it, it will not just shut off on you. It will give you enough room and even start notifying you, probably using an alarm. Some have inbuilt alarms that as much as I was designed to deliver 1,000 watts, I'm delivering extra. But if you find it useful, or if you find it necessary, or for my own safety, please unplug some of the components. Leave the essential or the critical components. So the base value is 950 watts. If we add our 50% safety margin to the 950 watts, what do we get? We get 1,425 watts. So the second value is the base value plus the safety margin, in bracket 50% of base. So that will be 1,400 and what? And 25 watts. So we are building our case slowly by slowly. This is what I want you to understand. We are building our case slowly by slowly. By the time we settle on the inverter, we will have known what this stage. At this particular point, if you go to the shop and ask for a 1,425 watt inverter, you're safe. As a technician, you are okay. For the client, he's safe. And then there's another third value that we should know. The inverter is operating at a certain efficiency. If the inverter is so, for example, let me explain it this way. When you convert energy from one form to another, some of it is lost during the process. An inverter is one of those devices or components or appliances that will convert energy from one form to another, DC to AC, AC to DC. Some of the inverters have got an all-in-one system that if it has been connected to the grid, it will pick AC from the grid, convert it into DC, and charge your batteries. When there's no grid and there's no solar, it needs to now release power back to your appliances. It converts the DC that is stored in your batteries, converts it into AC, and allows your appliances to run. So in a different lesson, we shall look at the DC coupled batteries and the AC coupled batteries, and just try and look at the efficiency of the two. But for now, let's look at the inverter efficiency. Let's say we are trying to get the most efficient inverter in the market. And we've realized that some of the manufacturers are delivering us inverters that are up to 95% efficient. some of the best manufacturers. Of course, those are premium manufacturers. So what this means is that if this inverter is picking, let's say 100 watts from the batteries, it will lose 5 watts and deliver 95 watts. That's a very basic example. If our inverter is 95% efficient, and it's supposed to deliver 1425 watts. Remember, that is the base value plus the safety margin. Please remember that. That is the base value plus the safety margin. If our inverter is 95% efficient, it's supposed to deliver 1425 watts. So we assume 1425 watts is equivalent to the 95%. This is the value at the end, at the output. At the input side of the inverter, it is peaking 100%. So what will be the input value? You take your 100%, you cross multiply. 100% multiplied by 1425 watts divided by 95%. So if you're fast enough, you will do it. You can comment if you're fast enough before I'm done. So that means we need an inverter rated at 1.5 kilowatts or 1500 watts. I hope I'm capable of explaining how we approached this figure, the 1500, which is equivalent to 1.5 kilowatt. At this stage, as a technician, this should be your most ideal value to work with. As a student, when you're responding to this question, you ensure that you explain it to your examiner or trainer or assessor that this is the preferred inverter efficiency. So how do you explain this to your examiner, client, trainer, or someone listening to you? You have calculated, you have listed the appliances in the house, you have confirmed their individual consumption in watts, you've listed it. The quantity of the appliances, this is to ensure that each and every appliance is catered for. So if you have a lamp, make sure all the lamps are catered for. And remember, under the quantity of appliances, pick each and every appliance on its own. If you have, for example, a laptop and a computer, for example, make sure you pick the wattage of the laptop and the wattage of the computer. Do not assume since this is a laptop and this is a computer, they're probably the same size electrons, so you just use a base value. No. For example, a house can have a radio, the ordinary radio, and it can have, let's say, a sound bus. It can have, probably somebody has another audio system somewhere, Bluetooth device in the bedroom somewhere. Ensure you cater for all that. Pick all that information and put it independently. The most efficient solar system is a solar system that caters for all loads independently, not as a whole. When we start looking at level 6, those who will advance and study solar installation, or those who will now study solar installation independently, we shall see how to calculate system sizing based on component, individual components, how they behave, and how to size a system based on that. So for example, we can have a system that has got a load that is probably 30 watts, but it's a capacitive load, and another load that is 200 watts, it's a resistive load. So how do we size this inverter to ensure that these components are being catered for independently, not as a whole? Because for us, for the standalone system, we are assuming this client is not going to load this inverter with some ridiculous loads. They're just the basic essential loads. So before I lose my line of thought, as a student, you've calculated your values, you've ensured that you've gotten the base value of the inverter, you list it. Make sure your examiner knows that this is the base value, this is the lowest value of the inverter size that can work, but that is not safe. So you introduce a safety margin of 50%. This is to ensure that in case the client missed or you missed a component or something else happens, immediately you finish installing, probably the client will call his friends to come and see his solar system. They'll want to watch TV for probably some more extra hours, and those friends will want to charge their phone. You have to cater for that safety margin. So you write it and you make sure that your examiner, invigilator, or whoever is looking at your work knows how you've approached this value. And then you go ahead and say, because this inverter is not operating at 100% efficiency, the amount of power that it will pick from the batteries and convert and deliver in AC will be lost. At some point, a percentage will be lost. So for my inverter to deliver 1425 watts, it needs to be able to pick 1500 watts. So make sure you cater for that, the inverter efficiency. And let's also use this. This is a very important value because we will use it again at the battery point, this preferred efficiency. So 95% inverter efficiency. I hope up to this point, I was confusing my students. I realized during the class session, I confused my students, and some of them were struggling to relate. Now, where do we add the, safety margin? Where do we add the efficiency, value? I was confusing them, and I realized later on that some of them were missing the point. So I done it again. I am explaining it so that they get it. Most of them were getting confused. But I hope now, because with the students of the academy, we just went through it once, and almost all of them got it. The TVET EDGE is open, so this is basically for the TVET EDGE and students of Butere Technical. Now, the inverter efficiency, let's keep this value in mind as we head over now to the battery bank sizing. So I hope that you will be able to see up there, but if you want, let me start from here, and I'll be mentioning some of the values critically so that you get them. No, so how do we get the battery bank? This is inverter sizing. This is battery bank sizing. So how do we know what capacity of battery bank do we need? Remember, we are operating in watt hours, kilowatts. Here we introduce a H. Be very careful. This is watt hours. This is just watts. The difference is this is equivalent to a gate, the watts. The inverter is equivalent to a gate. The bigger the gate, the larger the vehicle that can go through. All right? Or the bigger the gate, the larger the size of people that can go through. The gate analogy, with my students of Butere Technical, we used the supermarket analogy to understand the different roles of the components. And we said the inverter is equivalent to a gate that allows people to come into and out of the supermarket, the front gate. And the charge controller is the back gate that allows goods to come from the lorries into the store or into the shelves area. We used that analogy. So this inverter, this value here is equivalent to the size of your gate. The bigger the gate, the bigger the amount of people that can go through. This value here, the watt hours, is equivalent to now the amount of goods stored in the supermarket. That is now the direct comparison. So the bigger the value, direct comparison, the bigger the amount of goods in the supermarket. The smaller the value, the smaller the amount of goods in your supermarket. So how do we know how much or how many items or products or, size of products that you need to store in your supermarket? So let's calculate this. Now, we are assuming your inverter is supposed to pick this amount of power and deliver 8740 watt hours. I want us to get that very clearly. Your inverter is supposed to pick an X amount of power and deliver 8740 watt hours. So since the inverter is 95% efficient, it means it will pick a bigger value. Some will be lost through the conversion process, and this is what will be delivered. So let's find that value first. Let's find that value. Assuming 8740 watt hour is equals to the 95% delivered. What is the 100%? We cross multiply again. This is your time to shine. If you can get it faster than me, that is 8740 times 100 divided by 95. If you can get it faster than me, 8740 times 100, you have divide by 95. So that gives us 9,200. This is under now battery. We've started battery sizing. the process of battery sizing. So this is under battery sizing. So we have our first value, which is equivalent to 9,200 watt hours. All right. But most of our batteries are not, the battery rating, we don't use watt hours. In most cases, if me and you walk into a shop, if I say watt hours and I meet a technician who is a salesman, they'll do the calculation fast enough and they'll determine the size of the battery. But let's admit it that even traders now are selling solar products. There's nothing wrong with that. How do I explain to a trader that I need batteries that can be able to deliver 9,200 watt hours? So we need to find a value called AH value. And that is the value that we are aiming for. Remember, for our system, we are in East Africa and we do not have a shortage of sunlight. So we are going to size a system that will be capable of running from evening to morning. That is an equivalent of 12 hours. In the extreme cases, 24 hours. 24 hours, that's enough. We can run this system until the next time the sun comes out. But in most cases in East Africa, since we are blessed, if we size our system correctly, it will run from around 6 p.m. or 5 p.m., let's give it 5 p.m., all the way to 7 a.m. in the morning. And by around 7:38, there's enough sunshine to start charging your batteries. So let's go slowly by slowly. Now we have this value, 9,200 watt hours. Let me write a few things here, a few values or reference points, so that when we now start correlating how we are getting the values until we get the battery size, nobody's left behind, nobody's confused. So welcome back. For you, it's just been a second. For me, it's been 3 or 4 minutes. So I wanted to write this all down, guiding you through it. You should not feel confused. We have got 2 percentages here. These values were confusing my students, and I'll want them to watch this over and over and over for it to stick. There's this percentage here, 95% inverter efficiency, and then there's another percentage called the depth of discharge, the DOD. The depth of discharge means, depending on the battery technology, how much charge can you take out of the battery? How much charge can you take out of the battery? And this is what I mean. For example, for your phone battery, look at your phone battery right now. When you click up there, some phones will show you a percentage. That is the state of charge. Whatever is existing in the battery while you're using it, that is the state of charge. And state of charge is any value between 0% to 100%. So if your battery is fully charged, it is at 100% state of charge. If your battery is fully depleted, it is at 0% state of charge. And of course, most of us never allow our batteries to be depleted to 0% state of charge. The difference between state of charge and depth of discharge is this. If, for example, your battery is at 60%, let me write it. If, for example, the current state of a battery, when you click up, you see the current state of your battery. Let's say your battery is at 72%, right? What you're seeing. I hope there's a coincidence somewhere. Someone will watch this and their battery is actually at 72%. So let's say it's at 72%. That is the state of charge, which is equivalent to which is normally abbreviated as SOC. Now, the depth of this discharge that has occurred in that battery, you take 100% minus 72, you get 28. So technically, your battery has been discharged by 28%. That is not its maximum depth of discharge. It's only that it has been discharged by 28%. So for some batteries, you are allowed, for now, let's get back here. For some battery technologies, you are allowed to discharge them to 80%, meaning you are allowed to use that battery until its state of charge gets back to 20%. So from 100, you take it all the way to 20%. I hope I hope we get that right. The state of charge is what the battery is in the battery. When you go and test it and whatever now is remaining for you to take out again. The depth of discharge is the maximum that you can take out. So if it's at 100 and the maximum that you can take out is 80%, that means that the depth of discharge is equivalent to 80%. I hope that is well understood. So we have decided that we are going with a 94% efficient inverter, 95%, and the daily energy demand is equivalent to 8740 watt hour. This one, we've already predetermined that. The inverter input power, we've decided, how did we approach the inverter input power? Because the inverter is 95% efficient, it means it will peak power, a certain capacity of power, spend some of it during the conversion process, the electronics and whatever, some will be lost, and what it will deliver is 8740. So since this 8740 is your 95% on the output, on the input side, the inverter has to pick a bigger value. And so we found 9,200. So that is equivalent to the inverter input power, 9,200 watt hour. This value is not the size of the inverter. I was confusing my students and I noticed some of them were getting lost. The 9,200 watt hour is not equivalent to the size of the inverter. This is what the inverter will pick and deliver. This is what the inverter will allow to go through, right? So that means, to make you understand it better, this means because this is our gate, it could be wide open at 1.5 kilowatt, maximally wide open, but since not everything here is being used, we could say the daily energy demand could be less than 8,740. It could be, let's say, 5,000 watt hour. The inverter will allow 5,000 watt hour to go through easily, pass through. So let's understand it this way. We want to use a system voltage of, these voltages have been predetermined universally. We normally have a 12 volt system, the most common components 12 volts. Then we go to 24, next one, 36 plus 12, what do you get? 48. So we rise like that. But for the domestic market, the most common system components are normally rated at 12 volts. So how do we know the daily battery capacity that we need for a single day? One, remember we are sizing our system for 1 day. If we want to size it for 2 days, 3 days, 4 days, I'll show you where you change your values. Now, the number of days is equivalent to a variable, so I'll show you where you change it. So when you divide 9,200 watt hour, the inverter input power, divide by 12, you get 766.67 AH. Now we have moved from watt hour to AH. Please remember that. We have moved from watt hours to ampere hours. So this is now the universal standard language of batteries. Of course, if you are both technicians and you say, I want a battery that can deliver 9,200 watt hour, you do it very fast at the back of your head if you are fast enough. If you are not fast enough, check out your calculator, do it quickly, tell the technician what they need to hear. So we need a 766.67 AH, but that is not the standard or the actual size of battery that we need. We still need to calculate more. The days of autonomy. I explained that the days of autonomy is equivalent to the number of days in hours. We normally do our calculation in 24-hour cycles, right? So the number of days that this system can go without getting recharged. And if you go back, in our first video, I explained that if this system were a supermarket, it's equivalent to the number of days that people can walk into a supermarket and pick goods without the supermarket ordering the suppliers, the companies, to bring in the lorries. And we equated the lorries to the solar panels. So if you go back, there's another video, you can watch it. Although I made a mistake and recorded it in Sheng and Swahili at some point, but if you are interested, I can redo the video and re-explain some of those concepts. So the days of autonomy, let's say the days of autonomy for our system is 1. We have agreed why we are doing it with 1. Maximum depth of discharge, we have agreed we are going with a very modern system that can allow us to drain it to 80%. That means it can allow us to take away 80% of the charge and leave 20% next morning for the sun to start recharging it. So that means the battery capacity will be equivalent to the daily battery capacity, this times 1. And I explained, this one was confusing some of my students. I explained this one is equivalent to 24 hours, but don't multiply with 24, multiply with 1. I explained this and I saw some of them were struggling, but I hope now from the video, if you keep watching and watching and watching, it will stick into your brain that this one is equivalent to 24 hours. So don't multiply by 24, multiply by 1. If you want to 2 days of autonomy, you multiply by 2, not 48, as you go. Now, what will be our answer here? If you are fast enough, you can comment before I give out the answer. Go on the comment section and give me the answer before I do it. So that will be 766.67 times 1 divided by 80%. We get, what did you get? Say it out loud. I'm getting 958.3375 AH. 958.3375 AH. Did you get that? Has everyone gotten that? This is the value we are looking for, 958.337 AH. Now, at this point, there's another explanation that some of my students were struggling with. And so let me clarify. In a solar system, we are always looking for not to drain the system before the next charge cycle. And I explain what a charge cycle is. When you start, like the first time your system is installed, it's very rare for that system to come at 100%. The batteries will never come at 100% state of charge. They'll come probably at around 75, 80, 85% state of charge. Some will have drained to probably up to 60%. And I explained what a state of charge is. And I explained what a charge cycle is. A charge cycle a complete charge cycle only happens when a system, a battery bank system, a complete charge cycle only happens when a battery bank system is taken from 100% state of charge to 0% state of charge and then back to 100% state of charge. That is one cycle, depending on where you'll start from. If you start from 0, go all the way to 100, go all the way to 0. Like the essence is that at any given time, you've taken, you've put in 100% and you've taken away 100%. Ideally, it never happens like this. On paper, this is the calculation, but technically, in the real world, it never happens like this. And here is why. You are not allowed to drain your batteries to 0%. You are never allowed to size a system that will go all the way to 0% and then start the next morning at 0 to recharge back to 100. No. In most batteries, you are allowed to discharge 80%. That means you can take your batteries to as little as 20%. And in modern inverters, some of them have even been programmed to not allow you discharge beyond 80% depth of discharge. So let's use this example for you to understand what a charge cycle is. So if your battery is at 100% today, this evening, it's charged the whole day, no one is using it, and by 6 p.m., it's at 100% state of charge. Overnight, you plug in your appliances and they drain that battery to, let's give it a fair value, 40%. state of charge. You can find this figure probably on the inverter. Some inverters have been programmed to give you this value, so it will look at the voltage and other variables for it to tell you at what percentage this battery is. Same to your phone. Your phone will tell you what percentage your battery is, but technically a phone cannot go in there and see the percentage. It has to compare 2 or 3 values for it to determine that now this battery is at 40% or 50%. So assuming you've drained your solar system to 40%, not your solar system, your battery bank to 40%. 8 a.m. tomorrow morning, your battery is at 40%. You start the cycle of charging it. So technically here, you've only taken 60% out of this battery. This is one evening. This is the next morning. You've taken 60%. The next morning, you start charging it back from 40%, and because we've sized our system correctly, we shall learn how to size our charge controllers and our solar system correctly in our next lesson. So because we've sized our system correctly, the solar system takes this battery bank all the way back to 100% by evening, let's say by 5 or 6 p.m. Technically by 3 p.m. So it has, you have taken 60, you have added 60%, right? This is not yet a complete charge cycle. It's not. A complete charge cycle will only occur now. This is day 1, you've discharged. Second day, you've recharged, right? Now, on the evening of the second day, it's at 100%. You again start withdrawing or discharging. You pick enough or not enough, you pick, you get, you drain it to again 40%. That means you've taken away 60%, right? You've taken away 60%. So how do we know that our battery has reached one full charge cycle? You drained it 60%, you added 60, right? That's not yet 100%. You again drained 60, and so the next day now, you add another 60% to take it all the way back to 100. So in essence, if you take the brackets, you add the brackets until when the 100, the first 100 has been depleted to 100. Does that make sense? It's one, when you charge during the day, and this, if, for example, you size your batteries, just, and for example, in this case, let's say we don't introduce our 50% margin. The battery will still work, the system will still work, but this means you will have more charge cycles. More charge cycles means that every evening, when your battery is at 100%, in the morning, it's at extremely, at the lowest it can be. So if the lowest in our case is 20%, it means every evening your battery is at, or your battery bank is at 100%, every morning it's at 20%, every evening it's at 100%, every morning it's 100%, it's at 20%. What does that do to your battery banks? The process of charging and discharging involves some chemical reaction within the battery unit itself. A continuous charging cycle ensures that these chemical reactions degrade your battery faster than expected. If your battery is constantly charging and discharging, if it was meant to serve you for, let's say, 4,000 charge cycles, it might not be capable of going past 3,500 while delivering optimally. The first way of solving that issue is ensuring you have a bigger bank. A bigger bank means, if, for example, in the evening you are at 100%, in the morning you will not have drained all the way to 20%. you'll be having enough, let's say 40% or even 45%, not draining your system all the way to the bottom mark. That means you'll have lesser charge cycles, and the lesser charge cycles means your battery will last longer. If your batteries do not last, if your batteries are put on an extreme charging and discharging cycle, a continuous one, first, they degrade faster. I hope I've explained myself well. So at this point, if you wish to join our academy, you can reach out to. If you would like me to explain something in detail, if I've made a mistake in my calculation, we are open to criticism. Kindly explain where you think I made a mistake. Let me be guided so that in the next lesson, I might cover it and then we proceed. If you'd like to join the private classroom, the academy, share too. We will see how to guide you. We are offering these lessons both privately and publicly. There's enough information for the public. For the private students, we go deeper and understand systems now independently. For now, a student to understand the deeper workings of a system, they have to learn the basic parts, and then now we start, isolating a component and diving deep into it. So I'd like to thank you for today. I hope this has been a wonderful session. Let's meet next time.